All right, so here we go to start. All right, so this is the practice test for the test on Thursday, not Thursday, sorry, Wednesday. Some of the questions we did already, but I'm still gonna run through them question by question, all right? The multiple choice part, I hope you find it not challenging, but I don't want to say it's easy. I don't want to say it's hard. It's really, something that's depending on how you feel, all right? But some of it we've done already. So like the first, I guess some of the questions that talk about charge, they might seem familiar, I'm hoping. So let's see how it works. It says question 1, which of the following particles is not electrically charged? Pin this one, all right. And the correct answer here right, the correct answer here electrons are charged, negatively charged. Protons are positively charged. Positrons are positively charged. Positrons are like electrons, but they have a positive charge. Neutrons don't have a charge. So this would be the correct answer, right? Then if we looked at the second question, the area around the charged particle which can push or pull other charged particles, it would be fun if you guys try to see if you could beat me to the punch. What's the answer to this? What do we call the area around a charged particle that can push or pull other charges? Is it electric force, electric field, voltage, or resistance? A, B, C, or D? If you said the electric field, you would be correct, right? So the area around every charged particle is what we call the electric field, right? Happy, thank you. All right. And true or false, the nucleus of an atom is electrically positive. Is it true or is it false? I'll give you guys a little time. All right, I see that. So he says true. You are perfectly correct. Because only protons and neutrons are in the nucleus. Protons have positive charge, neutrons don't have a charge. So the net result is that the nucleus is positively charged, right? Question 4 says, when two positively charged particles are put near to each other, they will, and the responses are always push each other away. B says always pull each other. C says, sorry, exert no forces on each other, so no force between them. And D, all of the above are possible. So it's not D. Some of these things are like opposing, they're like contrary. It can't both be true. They're not mutually exclusive. So, all right, I was just waiting. A, they're gonna always push each other, all right? All right. And then 5 says two charged bodies, Q1 and Q2, are separated at a fixed distance R. If the size of Q1 is doubled, the electrical force on each body is now. That's a nice question. So you've got two charged bodies or two charged particles, Q1 and Q2. They're separated by a fixed distance. This question basically says, if you double one of the charges, so only one of them, Q1 is doubled, what happens to the electrical force? And you'd use this equation right here, right? Basically, you do something like this. What's the net result of doubling one of these charges? It's really F2 now being proportional to, instead of Q1, it would be 2 times Q1 times Q2 over R squared. Man, really? Is there undo for this? No undo. All right. Over R. Sorry. And sneeze. R squared. Now, if you look at this formula, I'm gonna use a different color. It's orange. This formula, and I'm gonna just highlight one part of this formula, this right here without the two, that is F1. So F1, remember, is Q1 times Q2 divided by R squared. So really and truly, I'm hoping you guys see this. This is me doing it in a longer way, but it's kind of making sense. Oh, you're not hearing? Is everybody, well, nobody's hearing me?
I hear you.
Oh, you hear? All right. Well, Nayeli, it might be check your speakers, I think. I'm hoping I'm coming out clearly. All right, I see those. So, all right, check and let me know in the chat if you can hear. All right, so F2 is going to be proportional to 2 times F1. The part in the yellow is F1, right? If you look at the above formula. So that means my response is going to be that it's going to double. Right? The only change is that you're like doubling one of the charges, right? And if you double just one of the charges, the force will double. All right. Part 7 says, which of the following definitions best describes the term, sorry.
Professor,
Yeah,
what's
question
that?
6.
The first six. Question 5. Okay, double.
Sorry. Double. And I actually skipped a question, so I'm actually happy you like paused me for a second. I was going a little too fast. Question 6 says, two charged bodies separated by distance R exert an electrical force on each other. When the distance is doubled, the electrical force, what happens to the electrical force, right? So this time I'm going to do the same thing, right? So I'm going to draw a new force or write down a new force. This force is going to be F2. And the only thing I'm going to do, I'm going to double. Okay, I'm going to double the distance, right? So it says when the distance is doubled, so I'm going to say F2 is proportional to Q1 times Q2. And this time I'm going to put on the bottom, instead of R squared, it's going to be 2R squared, right? Wait, and I should have really put a little space in between. So I'm going to do something like this. So I'm going to put a little bit of space. So it's 2R squared. And I did the same mistake. I'm sorry. 2R all squared, because now R is doubled, right? And then I'm going to do the same thing. You see that 2 that's beside the R? I'm going to take it outside, right? So I'm going to do something that looks like this. F2. By the way, you guys don't have to do this. This is like me showing you with math. I think some of you probably already know what the answer is. If you know what the answer is for this question, let me know. Does anybody know what the answer is here? I think you guys are probably seeing it now. I'm like doing the math of it. And then if you guys realize that this part that I'm putting in the bubble is what we defined as F1 up top, sorry, F up top, right? F equals Q1, Q2 over R squared, right? So if you look at it, and this is the one where I don't want you guys to be tricked. If you look at it, F2 is proportional to 1 over 4 F1. If you double the distance, the force gets smaller, but it doesn't like get smaller by like a half. It gets smaller by a quarter. So the correct answer for this one is right here. It's now 1/4 of its initial value. Right? Hopefully you guys are seeing it on the screen. I'm trying to make sure the math is there, right? All right. So I'll leave that right there for a little. Question 7 says, which of the following definitions best describes the term voltage? Voltage Is it the force on a charge in a circuit? No. Is it the total number of charges in a wire? No. Is it the number of charges that pass a certain point in a wire per second? See, all these definitions sound as if they could potentially be true, but there is one correct definition which has to do with energy. It's the energy per charge supplied by, and then that's one thing that you could use. It says battery or source. So that's one helpful thing right there. So it is D, the potential energy per charge supplied by the battery or source. Now, this is the one where I'm going to ask you guys and let me know. This one says true or false, all voltages or all voltage sources have two terminals. Is this true or false? Sorry. All right, I see true. You are perfectly correct, true, right? And you guys can think about it. You probably can think back at every kind of voltage source, batteries, car batteries, the sockets in your walls. Every single one of them has like two terminals, right? Sometimes you might see something that says ground. That's not necessarily a terminal. That's something that we use in circuit building, right? But every single voltage source has two terminals. Which of the following definitions best describes the term electric current? Is it, oops, sorry. Is it the total number of negative charges in a wire? That's not right. The total number of charges in a wire? That's not right either. Those just tell you the amount of charge. But if you remember, electric current is when you have charge that moves, right? So the third one, option C, says the number of charges that pass a certain point in a wire per second. That's the part that kind of highlights what electric current is. It's the rate at which charges are moving in a wire or in a conductor, right? So it has nothing to do with the potential energy. This one, D, we already defined this as voltage. Electric current has to do with charges moving in a conductor. And it has to do with the rate at which they're moving. How quickly are they moving? Correct answer is C, the number of charges that pass a certain point in a wire per second. And then 10 says, which of the following definitions best describes the term electrical resistance? Is it the number of charges that pass? Well, we already said A is electric current. Is it the total number of electrical components on a conductive path? No. Right? So you could have like 3 resistors and a light bulb that makes 4. That doesn't tell you anything about resistance. Option C, wait, is every single one of them C so far? All right, so there's a little bit of variance. Option C says a measure of the opposition to the flow of an electric current. This is the correct answer right here. Resistance, and you can kind of pin it, the definition to kind of the name. It's like electrical resistance. It means something is being resisted. So it's the opposition to the flow of an electric current, right? Right. So this is the tricky one, right? I think in the multiple choice, the next, I think, few questions, they're going to refer to this image, right? So these are the same kinds of batteries. So for no, because they're the same kind of batteries, and this question says they're all 3-volt batteries. What that means is that this is a 3-volt battery. These two are 3-volt batteries. And this is also a 3-volt battery, right? And then it also says the bulbs are the same. So the bulbs are 3 ohm bulbs. So it's 3. And then the symbol that we use for ohm is this one, the omega symbol. So it's 3 ohms. And these two are also 3 ohms. Right? Didn't do that one right. This is 3 ohm, right? And then our job is to like answer the questions that follow. So the first question says, which circuit has the brightest bulb? So You guys help me out. Which one of these circuits has the brightest bulb? I see B. All right. So this, you know what helps with this? The lab that we did, the more voltage you have is like you're dropping something from a higher height. So it moves like really well. Yeah, you can get the gist, right? I don't want to bring up like death or you're increasingly likely to die, but it is B. Why is it B? Because you have one bulb that's being supplied with three batteries, sorry, not three, two 3-volt batteries, right? And the bigger the voltage, the faster the charges are going to move around the circuit. So the more the current flow, and that leads to brighter bulbs. Now, the question is, which circuit has the dimmest bulb? All right, I see that. All right. Yeah, you guys been practicing. All right, it is C, and let me tell you why, because circuit 3 has the most resistance on the path, right? Think of resistance as like something kind of impeding the flow of the current. You can think of it as traffic on Christmas Eve, on Black Friday, or I don't know what day to think of. A very busy day where everybody's on the road, and the resistance would be like these stores having sales, sale on this, sale on that. Everybody's coming through. It's like a ton of resistance, right? So there's a ton of resistance along this path because there are two bulbs on it. And because there are two bulbs on it and it only has one voltage source, then that circuit is going to have the dimmest bulb. 13 says circuit 3 shows a circuit with bulbs in parallel arrangement. Is that true or false? And circuit 3 is this one right here. So is this a series or parallel arrangement? Remember, a series means that if a charge flowing in the circuit passes through one of the circuit elements, so one of the bulbs, it has to pass through the other. There's no option, right? So think of it as, let's say, water flowing in a pipe. And if water is flowing in a pipe, and I was going to use the bathrooms here at Essex County College. It's going to sound weird, but I don't even want to bring that up. No, let me not use that. Um, Series just means the same current flows through both bulbs. So all the charges that pass through one of the bulbs has to pass through the other bulb because there's no other option, right? And here, parallel also means, there is an option. So it's not in parallel. That would be false. All right. 14 says, what is the current flowing in circuit 1, right? And it gives us this little note right here, note voltage on the the right-hand side. It says note, remember voltage equals current multiplied by resistance. So here's what you do is, so a little bit of math here. The voltage equals, this is circuit 1. Circuit 1 is the one on the left-hand side, right? The voltage in that circuit is 3 volts. The resistance is because of the light bulb. The light bulb has a resistance of 3 ohms, and therefore the current that's flowing in that is V. Sorry, let me not do this. Let me do it how we normally do it. So I'll put a question sign right here. And then we go V equals I times R, which means current equals V over R, which is 1 volt divided by 1 ohm. And I saw the correct answer. Somebody had it up. I think that was Joan. I equals 1 ampere. So this would be the correct answer, right? So this is the first one where we have to do a little bit of calculation, right? But this one is easy. And the second one says, what is the current flowing in circuit 2? And before I do that, let me do a quick save of this file. Save. Yeah. Let's not lose all that so far. Circuit 2 is the middle circuit. It has two 3-volt batteries. And the question says, what is the current flowing in circuit 2? John, you say it's B. Let's see. All right, so we do the same thing as before. Voltage is two 3-volt batteries. So we're gonna get 6 volts. The resistance is because of one bulb, so it's 3 ohms. The current is what we're looking for, so I'll put a question sign. We know that voltage equals current multiplied by resistance, which means current equals voltage divided by resistance. And that means I could do this. I equals V over R, which is equal to, in this case, 6 volts divided by 3 ohms, and we're going to get 2 amperes. So the correct answer here is C. All right. The bigger the voltage, the more current passes through, right? You guys see that when going from circuit 1 to circuit 2. Circuit 1 had a 3-volt bulb. 3 volts connected to, sorry, a 3-volt source, battery source connected to a 3 ohm bulb. Circuit 2 has 6 volts connected to a 3 ohm bulb, and it has twice the current flowing. The third one says, sorry, not the third one, but the third like question like this says, what is the current flowing in circuit 3? Circuit 3 is the one that's on the right-hand side. And again, we're going to do the same thing, right? We are going to same thing. So here, circuit 3, if I go all the way up top, it's voltage, 3 volts. And here, I'm going to do something for the resistance. Just make sure you guys see this. Voltage equals 3 volts. Resistance, and I'm going to put T for total, equals 3 ohms plus 3 ohms, right? That's 6 ohms. And current equals, I'll put a question sign, right? Same thing as before. V equals I times R. Therefore, I equals V over R. And that V being the voltage, R being the resistance, and I is the current. V voltage, it's 3 volts. The resistance is 2 light bulbs, so it's 6 ohms. And this is the reason, by the way, why this circuit has the dimmest bulb, because it has the smallest resistance. Sorry, not the smallest resistance, it has the smallest current. The current flowing in this circuit is 1/2 of an ampere, or 0.5 amperes, and that would be A. Let me do a quick save. All right. All right. Question 17. Lightning is dangerous to humans because lightning strokes do what? Does it carry large currents? Does it have high voltages? Does it have no resistance? Or is it the fact that it's extremely bright? Is brightness a thing that's dangerous? I mean, brightness can, a lot of photons hitting your eyeballs, but I don't think that's the issue. I don't think it's the fact that it has no resistance. And it's not necessarily the fact that it has high voltages. Something that can have high voltage, and if you come properly dressed, you have on the right shoes, you don't, suffer from high voltages, right? High voltage is something that you can protect yourself from if you're wearing the appropriate, if you take the proper precautions. But high voltages lead to very large currents. And that's what you guys just saw in the previous three questions. The higher the voltage, the bigger the potential current. And the current is the thing that, can, really do damage, right? But those high currents come from high voltages. So whenever you see something that says high voltage, it means take precaution because this thing can pass a huge current through your body and that will cause problems. True or false? Switches and electrical fuses are used in electrical circuits to control the flow of electricity. Give it. Yeah, I felt that coming for like 10 seconds. Switches and electrical fuses are used in electrical circuits to control the flow of electricity, giving the ability to stop current flow when required. Is this true or false? All right. That is true. All right, another true or false. True or false, the direction of a magnetic field at a point can be determined by a compass. I see that coming in. Yeah, you are correct. This is true, right? So you guys realize we just switched to magnetism, right? So it switched from electricity and now it's like a lot of magnetic stuff. True or false, question 20, there are positive and negative magnetic charges analogous to positive and negative electric charges. I think we did this in class. I said that there is no equivalent in a sense to a positive charge. It's equivalent in a sense that they're like two things, but they're not equivalent because where you have charges and they can exist independent of the other charge. So a positive charge can exist independent of a negative charge, right? When you talk about magnetism, the poles can never exist independently. They're always in combination. So this one is false. All right. All right. Then question 21, true or false, a stationary electric charge produces a magnetic field around it. And this one, if you guys remember, I was saying in class, magnetism is something that results from motion, right? So you have to have things, you know what, when it comes to charges, I should say, you can have a stationary magnet. And the reason why you can have a magnet that's not moving and the magnet produces a magnetic field is because the charges inside of a magnet are already moving, right? But to have a magnetic field, you need to have charges in motion, whether it be inside of a magnet or just charges in a wire, there has to be motion. So you can't have a stationary charge producing a magnetic field. All right. True or false? Moving charges make magnetic fields. And based on what I just said, this is the one that's true. When you have a charge moving, it creates, this is the root cause of magnetic fields, by the way. The root cause of magnetic fields, it's really just a charge moving. Once the charge starts to move, a magnetic field is created. It could be moving in a battery, sorry, not in a battery, in a magnet, because that's what charges do. Huge synchronized swimming, billions of charges, no, not even billions, a lot. I want to say a lot of charges just moving in circles and they create a magnetic field, right? All right, so this one, I want you guys to help me with this one. This is another true or false, but I don't remember if we kind of dug deep into this. It says a changing magnetic field produces an electric field. Is this true or false? You guys let me know. All right, I see the correct answer is coming in. Everybody says true. This is true. Now, this is the funny thing, and this is the thing that would kind of set up the rest of this chapter, because the rest of this chapter is on electromagnetism, right? And it's gonna set up the fact that what I'm gonna say now has nothing to do with the test per se, right? But it was going to set up the fact that to create these fields or sustain these fields, you don't even really need a charge per se, right? Because a magnetic field can be used to create an electric field. And the last thing I was gonna do in class, I think, this was probably said, in not in great detail, but magnetic fields create electric fields, and then electric fields can be used to create magnetic fields. It sounds weird, but the last two things that I just said removes charges altogether, right? So you can have magnetic fields creating electric fields creating magnetic fields, but it just so happens that to do that, the fields must be changing in some ways. That sets up what's called electromagnetism and electromagnetic waves, but that's not required for this, right? Question 24 says, which of the following is not a benefit of an electromagnet or, sorry, over a permanent magnet? A says the magnetic field produced can be turned off. Which of the following is not a benefit, by the way? A is a benefit. The magnetic field can be turned off. That's the benefit. You might want to turn off the field, right? You want this thing to behave as a magnet, and then you don't. You can turn it off. The magnetic field strength can be increased. As it turns out, you can increase the magnetic field. You can create stronger and stronger magnets stronger and stronger magnetic fields or electromagnets by increasing the amount of current flowing through a wire. It is cheaper to build. That's also a plus. Magnets, real magnets, you actually have to go through a process of obtaining them, right? It's expensive. Electromagnets, you can buy a battery or a source, you can get some wires, turn the wires into a coil, voila, that's your electromagnet. D, it does not require a power source. Aha, this is the part that is the problem. Electromagnets require a power source. For you to get the magnetic field benefit from electromagnets all require currents flowing through some wires, and that current has to be powered by some power source, and that is the drawback, right? So every time, let's say you're building some door, a prison door, you want to keep the inmates in, and then PSCNG just decides, hey, we're gonna just shut off the power on this part of the grid, and then that's where your prison is. I'm joking. It's totally hypothetical, right? But then I'm just highlighting things to note, when dealing with electromagnets. Once the power is gone, magnetism gone, any benefit that you wanted to derive from having a magnetic field is also gone, right? So true or false, 25, two north poles will push each other away if brought close to each other. This is true. Question 26. Electricity and magnetism are independent phenomena. You guys tell me, is electricity and magnetism, are these independent things? Or are they connected? All right, that is false. And this is false. And I'll write just one word beside this that kind of tells you that these two things are not independent. And that word is electromagnetism. This would not be a word if these two things were independent, right? So electricity is something that you can study by itself. Magnetism is something that you can also study by itself, but the two things aren't independent. One affects the other, you know what I mean? So that would be false. 27, electricity and magnetism interact only when there is the motion of charges. This is true. I'm going to save this. 28, true or false, in a transverse wave on a string, particles on the string move up and this was the one that I said kind of held over, kind of crept into this paper. All right. So expect a brand new 28. I was thinking of it, but then totally forgot. Kind of slipped through the cracks. All right. 29. The primary function of an electric motor is, so this is the motor and the generator questions, right? If you guys don't remember this on the day, just think of the word generate, generate, generator, right? Generate meaning you're trying to produce energy, right? So the primary function of an electric generator is to convert mechanical energy to electrical energy, right? This is what power companies do, but they're going from chemical to mechanical to electrical. So they buy barrels of oil and then they go from chemical to mechanical. They turn these turbines, and then the turbines, they have like huge permanent magnet, and then the magnet is turned inside of some coil, and then we make use of this electromagnetism, the connection between the two, and we generate an electric current. The motor, think of motors as something that you're trying to get things to move. So this is going in the other direction. So you're converting electrical energy to mechanical energy. So cars have motors, the new EVs, they have electric motors. So they're going from electrical energy, which was stored in a battery, to mechanical energy. All right. Now we're in section 2. Second. All right. So question 1 in section 2 is all about us plugging in some values into this little equation right here, right? So it's all about calculating the actual force between two charged particles. So the question says 2-point charges Q1 and Q2. The values are there, right? One is, and I said I was going to do this. This symbol, mu, it really means times 10 to the minus 6. That's all it means, right? And the symbol C for centi, so that's this one right here. So it's 5 centimeters, means these symbols just means they're called prefixes. You could actually replace them with these things that I'm writing right here, times 10 to the minus 6, times 10 to the minus 3, milli for milligrams, right? For medicine, you'll hear milli a lot. That means times 10 to the minus 3, or 1/1000th off, right? I really should write that as well. So this one is really 1/1000th off, whatever comes next. Thank you. Man, I'm there writing. Thank you. So that's micro right here up the top, the first one, 70 and milli. So micro is the one that I think is probably going to be the one that's uncommon right now, right? Everybody knows centi because you've used rulers and you measured stuff in centimeters. That's 10 to the minus 2 or 1/100th of a meter. And then sometimes you pick up a drug and it says the drug is something in milligrams. And milli means 10 to the minus 3 or 1/1000th of, right? 1/1000th of a gram. This micro is 1/1,000,000th. So it's 1 divided by 1,000,000 of something, right? So here it's 1/1,000,000th of a coulomb. So for this question, this probably works, right? For this question, this is what we do, right? This is the equation that we're going to use. And what we want is a value for Q1, a value for Q2, and a value for R, right? And for part A, it's really just plugging those values into the equation, right? So it says calculate the force on Q2. Oh man, I see another typo. This should say Q1. All right, so I'll put that right there, all right? So it says calculate the force on charge Q2. So F equals, I'm sorry, let me not jump down. I just realized I didn't write down some of the stuff. Let's go with the givens, right? So this is A, Q1 equals 9.5 microcoulombs. All right. And remember I said one way of writing that is 9.5 times 10 to the minus 6 coulombs, right? Q2 equals 2.7 microcoulombs. And really that's 2.7 times 10 to the minus 6 coulombs. So it's 2.7 divided by 1 million, right? So it's 2.7 1/1,000,000th of a coulomb, right? And then the distance, I'm going to scroll down just a little bit. It says 5 centimeters. So that's R equals 5 centimeters or 5 times 10 to the minus 2 meters. Now, what we want is the force. And for this question, the force is going to be equal to this huge number, 9 times 10 to the 9, right? So it's a big number. This is actually like 9 billion, right? Times Q1 times Q2, and you put all of this over R squared. So this is the part that's tricky. The part that's tricky is not like writing down the numbers, right? The part that's tricky is actually plugging this in the calculator and making sure we get the right value, right? So it's 9 times 10 to the 9 multiplied by 9.5 times 10 to the minus 6 times 2.7 times 10 to the minus 6 divided by 5.0 times 10 to the minus 2 squared. All right, so here's how we're going to do it. I'm actually going to put that in a calculator with you guys. Let me jump to this. Uh, Desmos scientific calculator. All right, so ready. Let's do this. So it's going to be 9 times 10. I'm sorry, times 10 to the 9. All right, that's 1. With this, it's kind of cool because I could bracket these things. And then, oh, sorry, multiplied by, I think it was 9.5 and then 2.7, right? So it's multiplied by 9.5 times 10 to the, and this is the tricky part, and put minus 6. Oops. Times 2.7 times 10 to the minus 6. And then at the bottom, we're going to put 5 centimeters. So it's 5 times 10 to the minus 2. And then this is going to be squared. And if you look at the answer, we're going to get 92.34 newtons. Right? So this is kind of cool. It would be nice if all calculators would be like this. So you could just put it. By the way, the iPad has this nice thing where you could probably write this out, just like how it looks right here. And it tells you the answer, which I find pretty cool. I wish all calculators were like that. But final answer here for the force is 92.34 newtons. And then part B, believe it or not, part B is basically saying that was the force on charge Q2. What would be the force on charge Q1? And it says, try to state the force on charge Q1 without any kind of calculations. And then it says, all right, I see arrays not. Sorry, Joan, my bad.
Yes, Professor. I had a question.
Yeah,
So with the R, you had the 5 centimeters, 5 multiplied by 10 raised to power minus 2.
yeah.
On the top, if you scroll down or up,
Up.
yes, right there. Isn't that
Yeah.
the same M like the 10 raised to power 3?
Oh, you mean the M right here?
Yeah, isn't like that the same
Oh,
with
oh
the,
no.
okay.
All right, so I'm gonna make a distinction between these two things. So you got centimeter and then millimeter, right? So you see this one right here is the actual unit. That's the meter, right? And then these are what you call prefixes. A prefix is just, it's just these things right here. So I put prefix. So like I'm right here. I'll
Okay, so you're taking the whatever the power raised to is with the 10 with
yeah,
prefix.
yeah.
Okay.
So the in one of the, because it's centi, so I think like this would be a nice, man, it doesn't get any bigger. All right, let me do an easy one. Open image in tab. All right, this would be a nice one. So like whenever you see and then here's a messed up thing in physics. You see, we use the same symbol M for both milli, which is the prefix, and M again for the unit. And I think that messes things up when you're looking at it visually, right? You see M and it means prefix, and then you see another M and it means the unit. So you're like, which one is which, right? When you're seeing the pair of them together, the first one is the prefix, it means times 10 to the minus 3, and then the second one is the unit, which is the meter, right? But then if you see something like centimeters, which is this one right here, the C is the prefix, and then the M would be the meter. The C just means times 10 to the minus 2. Or it would be, sometimes you write it like this, or sometimes you put it as 1 over 100. But then you have a ton of prefixes. Some of them you hear in computing. So you probably heard about giga and megabytes and kilobytes, I think, or kilometers, micro, nano. Yeah, you probably hear some of these in medicine, right? Or stuff like that. But it's a common source of issues for a lot of people because, the symbols are the same, sadly. Um, but without doing any calculations, I could state that the force on charge Q1 is equal to minus 92.34. And you guys tell me, how do I know that? How am I sure that it's minus 92.34? There's a law in physics that tells me that this is the case. What law of physics is it? Oh, that's a good question. All right. The reason why I had to convert, by the way, from um centimeters to meters and from um microcoulombs to coulombs is because I want my final answer to be in newtons, right? So the answer for this kind of question is yes. So sorry, the question was, I don't know if everybody saw that. Do we have to convert? And the answer is yes. For this question, make sure to put in all those prefixes, the times 10 to the 9, the times 10 to the minus 6, and the times 10 to the minus 2, and you're sure that the answer is going to be in newtons. By the way, the reason for this is Newton's third law. Newton's third law says for every action or for every force that one object exerts on another object, the other object exerts an equal but opposite force, right? All right. Second. All right. So that's question one. Question two. Question two says state Ohm's law. This one is easy. This law says voltage equals current.
Can you go back a little bit?
Previous
Please?
one? No problem.
Thank you. I got it. Thank you.
Where was I? All right, voltage equals current. Voltage equals current. Why did I put an M? Voltage equals current. Oh, I was gonna put multiplied by resistance. This is V equals I times R. That's Ohm's law, right? So that's part A. Part B now says an experiment was done in which the voltage across a conductor was varied and the current through it recorded. The results are shown below. So you see this nice little thing going across, right? All right, this might be tricky, but I guarantee you guys, it's not gonna be, well, it's not hard, right? Seems tricky, but it's not hard. It says sketch a graph of current on the vertical axis divided by voltage, sorry, not divided by, against voltage on, let me do something that's big enough. A graph of current on the horizontal axis, sorry, on the vertical axis, and voltage on the horizontal axis. So this would be current I. This would be voltage. Say something like this, right? I goes up, V goes across, and then you put some numbers. So before I put the numbers, I'm going to look at what this is. So I do something like this, right? So I go 0.02. 0.04. It's a sketch, doesn't have to be perfect. 0.06. How am I getting these values? Oh, sorry. I'm getting these values from the actual table. This is 0.10. And this is 0.12. I put a little notch right here. Those are the I values in the table, right? And then for the V values, I'll do the same thing, right? By the way, this is 0 right here. On this side, I'll put 0.2, 0.4, 0.6, 0.8, 1.0, 1.2, right? All right. So it says to sketch. So we do something like this. We look at the first point. It's 0.02 to 0.20. So it's something like this. First point is gonna be right here. And for this one, I'll like let it small for just for a little bit, right? Second point, 0.04 to 0.4. Third point, 0.06 to 0.6, right? You see like this. And then 0.08 to 0.8. So I'll do some X's. And then 1.0 to, sorry, 0.1 to 1.0, just like this. And then 1.0.12 to 1.2. And then we just draw a line like this. Bam. That's part 1 finished. And then here's a cool thing. It says with the aid of the graph, determine the resistance of the conductor. This is where you'd use Ohm's law, right? Remember Ohm's law says V equals I over R. You could even do this from the table. So you could look at a table and you could look that every time you look at the I value and the V value, if you did this, by the way, R is equal to V over I. Every single time using the values in the table, you divide V by I, you should get 10. I'm not sure if you guys see it. And it happens for all of the values, right? So if I look at any value here, so I'll look at the first one, 0.20 was the voltage, and the current was 0.020. And that means R has a value of 10 ohms. And that happens for every single one of them, right? So this is what you do for this kind of question. It's just to sketch the graph. It tells you which one should go on the vertical axis, which one should go on the horizontal axis. A sketch means it doesn't have to look pretty. It could look exactly like what you're seeing right here. It just needs to show the gist, right? How does everything, how give an idea of what it looks like. Doesn't have to be perfect, right? So this is cool. You don't even have to have those dashed lines either. I just put it in there just because I want you guys to see where I'm headed, right? Everybody cool with this one? This one is kind of new. But is everybody cool with this one? Give me like a thumbs up. Right? And then the last one. All right, so this is third question. It says a bar magnet is shown in the drawing below. Complete the drawing by including lines with arrows that illustrates the bar's magnetic field. Now, this is what I want you guys to do if you saw this, right? So you draw lines that look like loops. I always call this the butterfly, by the way. The reason why I call it butterfly is because it has these two lines right here that look like antennas, kind of, on the other side as well. And then the other side of the butterfly. This is the magnetic field. And then here's a part that, we should never forget, the arrows. So they always point away from the North Pole and towards the South Pole. So you put a few arrows in just to indicate that it's going away from the north and towards the south, right? So you put in these arrows like this, it's coming out like that. It's going in like this. In, and in, all right? That's it. That's the magnetic field, right? Illustrated using magnetic field lines. It doesn't have to be perfect either, right? And just to illustrate this, I'll probably put it up here. Show you what you're trying to draw. Magnetic field of bar magnet. All right. This is what you're trying to draw, really, right? Image in a new tab. All right, so this is what you're trying to draw, right? As best as you can, right? It doesn't have to be perfect. Remember, it's a sketch. So this sketch is cool. As a matter of fact, I'll say this is a pretty good sketch. And then this part, it says in less than 2 paragraphs, describe the purpose of a transformer and how it works. So this is like the last thing I was doing in the previous class. So now I feel bad that the last thing that we did has an entire part B. And I really feel bad about this, but yeah, I heard some things have to be on the test. All right, so what is a transformer? How does it work? All right, so you put something like this. The purpose of a transformer is to step up. So I'm going to use a term that's normally used. And then in brackets, I'm going to put something that makes sense. Increase the voltage. So step up or increase the voltage of a voltage source, or step down. I'm going to say decrease the voltage of a voltage source. Sorry, voltage source. What transformers do is it increases the voltage or decreases it. And I'm gonna kind of do something here, right? So I'm gonna draw something like this. And then I'm gonna draw another thing like this. These are 2 coils. Coil 1, and this is coil 2. This could be your input coil, and this is the output coil. And then these, I'm gonna put something here, N, I. This is number of turns. Man. So when I say number of turns, I mean how many times is the wire looped around? This is NO for output. And then this is the number of turns on this side, number of turns. And then these coils would be connected to some voltage. This is VI. And over here would be side would be VO, and we'd use this equation. This equation is right here at the top. So you'd say something like this: voltage is stepped up or down, man, depending on the number of turns in the transformer's input and output coils, right? Now, you guys might ask, what is a coil? So I'll show you an image. A coil is just wires spun around in circles. So here is a nice example. All these are examples of coils, right? All these are coils. And then I'm gonna give you transformer coil. So this, remember I said to you guys that if you guys ever decide to break open the adapters for your phones or gadgets, this is what you'd see inside, right? It's very, well, for the adapter, it's gonna be very small. Maybe I'll save you the trouble of breaking it open. Let me see if I could find a picture of one of these things inside of your adapters, so you don't have to. So these adapters right here, see, it says AC DC adapter, the thing that you plug into the wall and you plug in the other side to the phone, they have these nice, yeah, here is one right here. This is a transformer. So if you guys, I was gonna say ever decide to break it open, but I don't want you to break it open, so let me not say that, right? But if you guys ever see inside of one, this is what it's gonna, you're gonna see a transformer in there, because when you plug something into the wall supplies 110 volts, but your device requires 12 volts, doesn't require 110, right? And in order to get the voltage to 12, it has to be stepped down. So at the end of this, voltage is stepped down, step up, sorry, or step down, depending on the number of turns in the transformer's input and output coils. And that's based on this equation, VO over VI equals NO over NI. And that's it. I'm gonna save this, and I'm gonna put this on Moodle. All right, how do you guys feel? This is where I try to get some feedback.
Professor, I just have a question. Where you have NI, that is number of what? I'm sorry.
Sorry, that's the number of turns, the
Okay.
number of times the wire is looped around for the input coil. So that's the coil on the left. So it's like you could get coils with different number of turns. So I'm gonna put some here. Coils with number of turns. I want you guys to be able to visualize what this looks like. So let me choose some images. I'm sorry, I have a Pascal coil with this. I'm gonna put Pascal. The one that we have in the physics lab looks something like this. And actually, by the way, this is your transformer right here, right, in this picture, but I'll show you the coils first, right? So sometimes the coils will tell you the number of turns, the number of times the wire is spun around. So this one is showing you a coil where the wire is looped around 1,600 times, right? And then this one, whoa, this one right here, all right, just visit, shows a coil where the wire is looped around just 200 times. And then you could use two of these to make a transformer just by putting the coils right beside each other, right? Just like this. And then if you pass a current through one of the coils, based on the number of turns on one side, the input, and the number of turns on the other side, you could step up the voltage or step it down based on this equation, right? So let's say, I'll use some values. Let's say you wanted to step up the voltage. Let's say you had a 12-volt source, but you wanted to, let's say you had a 10-volt source and you wanted the 10-volt source to become 100, right? This is what you do. So this part, I don't even know where to write this. This part, oh yeah, I'll put it right here. So you'd use a coil that looks like this. I'll get a coil. This is the input coil right here. It would have, let's say, 100 turns. And then I'll get an output coil. And this one would have 1,000 turns. And I would have my 10 volt input source right here, 10 volts. And then this is what would happen. I want to calculate V output. So I'll do this. V output would be equal to NO divided by NI times VI. That is 1,000 turns on the output coil divided by 100 turns on the input coil multiplied by 10. And that has the effect of stepping up the voltage to from 10 volts to 100 volts. So this is an example of a step up transformer. Wait, can you guys hear me?
Yes,
Yes,
Professor.
Professor.
All right, just making sure. Sorry, just making sure. This is largely it. So this is the thing that I mostly want you guys to restrain yourselves to study. Largely this, and then after you figured out all of this, then you can kind of, if you want, kind of creep over on the slides and on the videos, but focus on this first and then the videos and the slides. Everybody cool with that?
Yes, thank you, Professor.
All right, I'm gonna stop right here for many reasons. One, I'm not feeling so good. And then two, I actually have a slight emergency. But I'm gonna put this on Moodle in probably 1 hour. Hopefully everybody's cool with that. So this exact file, I'll put it up probably in an hour, right? And you guys can use it for preparation, right? Print it if you need it, but then you guys can use it.
Thank you,
All right.
Professor.
So I'll stop right here. I'll put the video up as well pretty soon, but you guys will see it in a little bit.